And then you
Everyone, my name is Nanaya Intudi. I'm a second year electrical engineering student. Now, this YouTube channel is the ELEESA YouTube channel on your
Hello, good morning. I'm Salah and I'll be your tutor for applied electricity. A second year electrical engineering student, a member of the ELEESA academic board. And before this video starts, I will wait from you from our very own Nanaya Intudi, a member of the ELEESA board.
Everyone, my name is Nanaya Intudi. I'm a second year student. Now, this YouTube channel is the ELEESA YouTube channel and you're welcome here. I believe that this YouTube channel is a very good initiative from the academic board of the ELEESA department. I urge you all to try and take the videos here very seriously. Watch and don't be selfish. Share to all your friends across the engineering department. Don't forget to turn on your post notification button so you are alerted anytime a video is out. And don't forget to like, subscribe, comment all your views, anything on your mind, just comment, and we are here to help you. Bye. Hi everyone, my name is Nanaya Intudi. I'm a second year electrical engineering student. Now, this YouTube channel is the ELEESA YouTube channel and you're welcome here. I believe that this YouTube channel is a very good initiative from the academic board of the ELEESA department. I urge you all to try and take the videos here very seriously. Watch and don't be selfish. Share to all your friends across the engineering department. Don't forget to turn on your post notification button so you are alerted anytime a video is out. And don't forget to like, subscribe, comment all your views, anything on your mind, just comment, and we are here to help you. Bye. Hi everyone, my name is Nanaya Intudi. I'm a second year electrical engineering student. Now, this YouTube channel is the ELEESA YouTube channel and you're welcome here. I believe that this YouTube channel is a very good initiative from the academic board.
Okay, so on your last tutorial, I think you treated voltage division, current division, and the so today basically we would move a step ahead, right? But before we move, I want you to recall what you did last week. 1, 2, 3. So we start from voltage drop. So the concept of voltage drop is okay. So what's voltage drop? That's the very first question. What is voltage drop? So voltage drop is basically the amount of voltage loss that occurs through all or basically parts of a circuit, an electronic circuit, when the current flows through a resistor. Right. So for voltage drop to occur, then there must be a resistor, right, or an impedance, because you have an inductor, we have a capacitor, and then we have a resistor. Alright, so there must be current flowing across the components that has this impedance for voltage drop to occur. So let's take like this circuit. Let's say we have a circuit with alright. Let's say we have a circuit okay. So something basically of this sort. Alright. So if there is this is the voltage source, right? V. Alright. So there is a voltage that this source is producing. Alright. So as current flows through to this point, there is going to be a drop in this. Alright. Since I have just one component here, you realize the voltage across this is basically going to be the voltage across this. But assuming there is another resistor here, alright, then the voltage, there's going to be a voltage drop across this resistor, and there's going to be another voltage drop across this resistor. All we get. So if this is V1, then this, let's say V2. All right. So the source voltage, current flows through this to this particular resistor, and there is a drop. Current flows through this as well, and there is a drop. Now the sum of voltages across these two resistors is basically going to be equal to this voltage here. I believe you know this from high school. Okay. So let's liken the concept of voltage drop to, let's say, watering a garden. Sorry. Okay. So we're watering a garden. We have holes with water flowing through this particular hose. Right. Now, depending on the size of the hose, the pressure with which the water comes will also be determined, right? So if I have a bigger hose, then it means the water flows like really kind of. So the water from wherever we are pumping it has a free move through the hole depending on the size. So if there are lots of components in this circuit with their own impedance, realize there's going to be lots of voltage drops, and all these voltage drops sum up to the voltage of the source, or basically the source voltage, right? Yeah. So let me take a question. So let's say we have this to be our electric circuit, all right? And I give you the source voltage to probably, let's say, 15 volts, right? And then this resistor here has, let's say, resistance of 2 ohms, right? This has, let's say, current flowing through it to be, say, 5 amps, all right? Say a current of 5 amps flowing through it. Now realize these two components are in series, all right? So the current flowing through them should basically be the same. This tells us that the current across this 2 ohm resistor is equal to the current across this resistor of unknown value, all right? And we treated the concept of voltage drop, saying that the voltage across this resistor and the voltage across this resistor sum up to the source voltage, all right? So if I ask you to find the value of this resistor, right, I think you should be able to do it, because we know the voltage. So voltage basically equals the current times the resistance, right? So it means if this is V1, this is V2, then V1 plus V2 should be equal to 15, right? Right, sure. So V1 plus V2 should be equal to 15. So from here, we know the current flowing through the 2 ohm resistor. So we can find the voltage drop across the 2 ohm resistor to be what? 5 times 2, right? That's the voltage drop across the 2 ohm resistor. So V1 is basically 10 volts, right? So if you have to find V1, then you know V1 is 10 volts. Now, what is the voltage across the 5 ohm, the other resistor, which is V2? So V2 is going to be equal to 15 minus 10, which is 5 volts. So if V2 is 5 volts, then what is the value of the resistor having this voltage drop of 5 volts? All right, that's the next question. So if V2 is 5 volts, so V2 is equal to the current through the 5 ohm resistor times the impedance across, or the resistance of that 5 ohm resistor. So let's say that resistor, so let's say it's R, right? And we have V2 to be 5, then I to be 5, so 5R. So it means that resistance is 5 on 5, which is 1 ohm basically. All right, so the resistor, so the resistor in this circuit, the unknown resistor here is 1 ohm resistor. So this is basically the concept of voltage drop. Sure. So I hope you get it. If you have any questions, you can ask. So the next thing we would deal with be the Kirchhoff laws. All right. So we have Kirchhoff voltage law, then Kirchhoff current law. So let's say KCL and KVL respectively. KV. Sorry. So KCL and KVL. Right. So Kirchhoff current law and Kirchhoff's voltage law. So what's Kirchhoff's current law, or what does the law state? So Kirchhoff's current law basically states that the algebraic sum of the currents about a node, all right, that's the part I want us to take care of. Right? Take the currents, the algebraic sum of the currents about a node is 0, all right, or the currents entering a junction is equal to the currents leaving the junction. All right, yeah. I think you treated nodes, junctions, mentioned others the other time, so you know what I'm talking about, right? So the currents entering a junction is equal to the sum of currents leaving the junction, or the algebraic sum of the currents about a node, 0. Right? So one thing I want you to take note about Kirchhoff's current law is that it basically deals with nodes, and it deals with the conservation of charges. All right, charges. You know that charge is equal to the current times the time, right? Q equals IT. I believe you know that. Yeah. So Kirchhoff's current law deals with conservation of charges, right? So if you see this in any of the MCQs, then you should go for charges and not energy. All right. So when you get to Kirchhoff's voltage law, realize Kirchhoff's voltage law deals with conservation of energy, right? Because it deals with the potential differences. All right. So I'll take some questions on Kirchhoff's current. You should know that Kirchhoff's laws can actually be applied to all circuits, like linear circuits, non-linear circuits, and then biplanar circuits. Yeah. So let me get a question on Kirchhoff's current. All right. So let's take this question for instance. So this we have I here. So basically, what is the value of I? That's what this question is asking us to do. So what is I here? So it means the sum of currents entering the junction should be equal to the sum of currents leaving the junction. That is what we're going to do. We're going to use that concept to find the value for I. Now realize this 3 amp current is moving towards this node, right? 2 amp moving towards. This is moving away, right? So from this part, you have the 3 amp, which is entering, plus the 2 amps, alright? With directions, you can make some positive, some negative, depending on your conversion, right? But I would make the ones moving towards the junction positive, and then the current leaving the junction to be negative, right? So we have 3 plus 2, this 5. So we have 5 amps of current entering this particular junction, right? And then minus I, right? Because I is leaving the junction. Okay. Now let's come to this branch as well. So we have 2 amps entering, 5 amps entering, and then 4 amps leaving. Alright. So we have 2 plus 5, 4 amps leaving, so minus 4. Right. So we have 7 minus 4, which is basically 3. Right. Okay. So if this should be equal to this, right, then what is the value for I? So I is basically going to be equal to 5 minus 3, and now I is going to be 2 ohms. So I have a value for I to be 2 ohms. So this is the whole concept of KCL or Kirchhoff's current law. It's nothing. It's a big deal. So let's try the next question. Okay. Alright, so with this, we just want to form an equation for I. Alright, so for the voltage drop, sure. And then you want me to revise it. So okay. So basically, voltage drop. It said the voltage drop is the amount of voltage loss, alright, that occurs through the components in an electrical circuit caused by the impedance of those components. Alright. So for voltage drop to occur, I stated earlier on that there must be an impedance. Alright. So I didn't use resistance because we have a resistor, we have an inductor, we have a capacitor. Alright. So they all have their various impedances. Okay. So voltage drop occurs due to the impedance of these components within the circuit. Right. And I stated that the sum of voltage drop across all these components is equal to the source voltage. Right. So with this particular question, we have the voltage across this to be V1 and the voltage across this to be V2. Right. And I stated that if the voltage drop across this is V1, across this is V2, then the sum of these voltages is equal to the source voltage, which is V, right? And I gave a question where we had a 2 ohm resistor and a resistor of unknown value in series. Alright, we had our source voltage to be 15 volts. Right, so I gave the current passing through this components to be 5 ohms. Right, now we know the 2 ohm resistor and this resistance of unknown value are in series, so basically the current passing through them should be the same. Then you did series and then parallel resistance the other time. Okay, so if the voltage, the source voltage is 15 volts, that means the source voltage is equal to the voltage drop across these 2 resistors. Alright, now if I know the current passing through the 2 ohm resistor, then I can find the voltage drop across the 2 ohm resistor, which we found to be 10 volts. Alright, right here, 10 volts. So if the voltage drop across the 2 ohm resistor is 10 volts, then what's the voltage drop across the unknown resistor? We found that to be 5 volts. Right, now after finding that, we know the voltage is equal to the current times the resistance. Right, so if the voltage drop across the unknown resistor is 5 volts and the current passing through it is 5 ohms, then the resistance of that unknown resistor is 1 ohm. Hope it's clear now. Sure. Then we moved to Kirchhoff's laws. Right, so we started with Kirchhoff's current law. So Kirchhoff's current law, which I stated as the sum of currents entering a junction is equal to the sum of currents leaving a junction, or the algebraic sum of currents about a node is 0. Alright, I said Kirchhoff's current law deals with the conservation of charges. Alright, and also it can be used for in linear circuits, in non-linear circuits, linear or planar circuits, non-linear or non-planar circuits. Right. Okay. Then I gave a question where we have to find the current using Kirchhoff's current laws. Right. So with this, we have to find I. And working, we realize I is 2 ohms. How we go with all this? Okay. So I'll move to Kirchhoff's current law, right, which is voltage law, which is KVL. Okay, so we're here. Sure. So we're here. So we wanted to form equations for these currents about this particular node. Alright, so we wanted to form equations for this. Assuming we're given the values of sum and asked to find the other. Yeah. So I1 is entering the junction. I2 is leaving the junction. I3 is entering the junction. I4 is leaving, and I5 is also entering. Right. So we said the sum of currents entering the junction is equal to the sum of currents leaving the junction. Right. If that be the case, then I'll make with my convention, right, which is the general convention. The currents entering the junction denoted positive and those leaving negative. Alright, sure. So sum of currents entering the junction. So I have I1, sorry. So I have I1 plus which other one is entering? I3, right? Plus I5 is also entering. This should be equal to I2 is leaving, I6 is leaving, I4 is also leaving. So yeah. Alright. So this basically the equation we have. So I1 plus I2 plus I3, which is the sum of currents entering the junction, should be equal to the sum of currents leaving the junction. Alright. So I2 plus I4 plus I6. Okay. So that's Kirchhoff's current law. Okay. So I'll move to Kirchhoff's voltage law. Alright. So Kirchhoff's voltage law states that for a closed loop, right? So yeah, so Kirchhoff's voltage law. So for a closed electrical circuit, the algebraic sum potential difference about that loop is right? Opposed to the algebraic sum of potential difference about that particular loop is 0, right? Yeah. So and I think you did what loops were the other time also. So let's say I label this as A, B, C, D, E, F, G, H. Alright. So you know A, B, G, H, A is a loop, right? Then B, C, F, G, E is another loop. I'll be well. Sure. Then C, D, E, F, C is also a loop. So the algebraic sum of potential difference across this loop is 0. Alright. So if I take this very loop, right? If I take this very loop, the algebraic sum of potential difference about this loop 0. If I take this loop as well, sum of potential difference here is also 0. The same applies to this. Alright. So if I ask you to find the currents flowing through any of these components, alright, now you should know you're going to use KCL and KVL because you need KCL to distribute your currents from the source, and you need KVL to find the potential difference about like the potential difference across the various components, right? And you're going to use the loop system for this. So we'll solve this question using KVL and KCL for my please, I hope you get what we're doing. Okay, so as someone was asking me to state the KVL in terms of EMFs, right? Sure. Okay, so I'll just write it here. So the oh, sorry. All right. So the sum of voltage drop across the components in a loop, right, is equal to the voltage across the sources, right, which is basically the EMF of the sources. So getting back to this diagram, right, now this is the source voltage, right, or the EMF produced here. So the voltage drop across this plus the voltage drop across this is equal to source voltage, the EMF produced by the source. I hope that makes sense. Yeah. So basically the sum of voltage drops about a loop is equal to the sum of EMFs on the source voltages. Alright. Sure. So we solve this question. Then CL, then KVL. So let's assume we ask to find the voltage produced. Sorry, we have to find the current that this 12 volt source produces, right? So I'll label my current from the 12 volt source as, say, I, right? So if I label my current from this source as I, now when I gets to this particular junction, right, distributes it to, so let me say this is I1, right? Now if this is I1, then let's say this is I2. So I2 basically is going to be, so I2 basically equals I minus I1, right? So I can just write I minus I1 at this side, right? Now like this, two resistors are in parallel connection, alright? So I can just find the effective resistance and then simplify my circuit. So my circuit can be simplified as, so if this is my 12 volt source, then this resistors are in parallel, so 3 times 2 on 3 plus 2, right? So I have, there's a resistor here. So I have the resistor here to be in 6 and 5, right? And I have a 4 ohm resistor here, and I have a 3 ohm resistor here, and I have a 12 volt source here. I hope you get it. Sure. So if I want to use, so this is I1, this is I minus I1. Oh, sorry, this is, yeah, I1. So I minus I1, and this is I. Right. So if I want to use ACL, then about this loop, we're moving from the positive terminal to the negative terminal. Right. So the 12 volts source is equal to the voltage drop across this two resistors. That's the 3 ohm resistor and then the 4 ohm resistor. And the voltage drop across the 3 ohm resistor is going to be 3 times the current across the 3 ohm resistor, which is 3 times I, right? And the voltage drop across the 4 ohm resistor is going to be 4 times the current across it, which is 4 times I1, right? So this is the first equation that we have. Now, with this loop as well, right, moving from the positive terminal right to the negative terminal, our 12 volt source is also equal to the voltage drop across this 3 ohm resistor, which is 3I plus the voltage drop across this 6 on 5 ohm resistor, which is 6 on 5 multiplying I1. Sure. So we have two equations to solve here. 12 equals 3I plus 4I1. Then 12 equals 3I. So 3I plus 6 on 5I. So 3 plus 6 on 5 here. That's 21 on 5. So 21 and 6 on 5 I1. So let's solve these two equations for I and then I1. Then we'll get our value for I, which is the source current, to be whatever value we have. So please, someone should punch this into the calculator and then give me the value for I and then I1. Okay, so I think we'll get a value for I1 to be 3.06 amps, right? So that's the source current, or the current produced by the 12 volts source, right? Sure. So that's KVL. Yeah, that's basically what KVL is about. So we'll take this question as well, solve it, and then to enlighten ourselves more on ACO and KVL, right? Okay, so I think we'll get some. All right, so this is our next question. We have to find I. So this is I, right? We have to find I in this circuit. Sure. The circuit looks a bit complex, so we want to reduce it to a very simplified something, and then we work with it. Sure. So now when you take notes, you realize the 5 ohm resistor here, the 7 ohm resistor, and then this 3.5 ohm resistor are all short circuited. I think you treated short circuits, open circuits the other time. Okay. So realize this 3.5 ohm resistor, this 5 ohm resistor, the 7 ohm resistor are all short circuited. Right. So we can draw an equivalent circuit where these resistors won't be part of our circuit diagram. Alright. So they will all be taken off. So I won't draw a new diagram, I'll just modify what is here. Yes. Sure. So this is where everything ends. Everything ends here, right? Let me just take this off. So all of this are out, right? This part of the circuit is out because it's short circuited, right? So we now have a circuit diagram containing 4 ohm resistor, a 1 ohm resistor, 2 ohm resistor, and then a 3 ohm resistor, right? Two resistors are in parallel connection, right? The effective resistor is going to be 6 on 5, as you can see, right? Sure. All right. So these two resistors are in parallel, right? Sure. So we have 2 ohm resistor in parallel with a 3 ohm resistor, right? And then, okay, sure. So that gives us 6.5 ohms, right? So we can redraw a circuit diagram So we had a 4 ohm resistor here, 25 volt source, a 1 ohm resistor, and a 6.5 ohm resistor. Sure. So we have a 25 volts source here, a 1 ohm resistor, and now we have a 6.5 ohm resistor. All right. Now we have to find I, which is current flowing through the 4 ohms resistor. Right. Now before we find I, we must know the current that the 25 volt source produce. Right. That's the first thing we must take note of. So to find the current that the 25 volt source is producing, that means we must find the effective resistance. Alright. Sure. Now realize this 4 ohm resistor is in parallel connection with the 6.5 ohm resistor. Alright. Okay. So we have 4 ohm resistor in parallel with 6.5 ohm resistor. And this combination is in series with the 1 ohm resistor. I hope you get it. Sure. So 4 by 6 on 5 on 4 plus 6 on 5 plus 1. Right? What does this give us? So let's finish. So we have 25 on 13. Alright. So we have our effective resistance to be 25 on 13. And that's the total resistance. Alright. So we now have our circuit diagram reduced to 25 on 13, 25 volts. Right. Okay. There are problems, I think we would have to go back and check. So we have 4 times 6 on 5. 6. This plus 1. Yeah. Okay. So I think that is it. Sorry. Okay. So this is what we have. Meaning the current flowing through, or the source current, right, is, so V equals IR. So I equals V over R, which is 25 times 13 on 25, right, which is 13 ohms. So the source current is 13 ohms, right? So the current that this 25 volt source produces is 13 ohms. But that's not what we're asked to find. We're actually asked to find current passing through the 4 ohm resistor, right? So we'd have to employ current division rule here. I believe we did that last week as well. Sure. So you have to employ current division rule to find the current across this. So we have 13. So let's say I, alright. So I is going to be equal to 13 multiplying. Now we are finding the current passing through the 4 ohm resistor. Alright, so we use the resistor in the other branch. So the effective resistor in this branch is 6.5. Alright. So 6 on 5 is divided by 4 plus 6 on 5. Right. So we have I to be equal to 13 multiplying 6 on 5 on 4 plus 6 on 5. Right. So this is what we have. And what's our value for I? That's 3. So I is 3 ohms. So meaning the current passing through this 4 ohm resistor is 3 ohms, right? The current across the 4 ohm resistor, which is I, is 3 ohms. Okay. So that's how we go by this particular question. I think we are okay with the current division rule. Assuming we wanted to use KCL, right, to find the current across the 4 ohm resistor, right? After drawing this circuit diagram, everything becomes simple. So taking this loop, right, then 25, sorry. So I will draw the circuit diagram, and then we have a 4 ohm resistor. We have 1, we have 4 ohm, and we have 25 volt source here, right? So now we have this loop, then we have this loop, right? So if this is I, which we have to find, right? Now we could make this one I1. And looking at it, this becomes I plus I1. I hope you're okay with this. Sure. So with the first loop, we have 25 to be equal to, okay, so our loop goes this way. So our loop goes in the opposite direction to the I, right? So we have minus 4I plus I1, right? Then with this as well, so our loop is moves in the same direction with all of this. So 25 equals I1 plus 6 on 5 multiplying I plus I1. And we solve these two equations for I. Yeah. So we have 25 was I1 minus 4I. And then 25 equals, so I1 plus 6 on 5I, that's 11 on 5. 6 on 5I. Alright, so we solve these two equations simultaneously for I and I1. So we have I1 to be equal to 13, then I to be equal to minus 3. Then we have to come back. Okay. Okay. It's 15 minutes. 15 minutes. Yeah, so I think that's basically it, right? So that's it for KVL. right? The next thing will be looking at the circuit theorems, right? So there are basically several circuit theorems, but for this particular course, I think we'll be touching a few. Right? Then as we go ahead, the others will be talked about, right? So circuit theorems. So we have the Thevenin's theorem, right? We have the Norton's theorem, right? We have superposition theorem. We have reciprocity, right? Reciprocity theorem. We have intelligence and any others, right? But basically, we'll be dealing with Terminus theorem for this particular course as in today's tutorials, right? So let me just rush you through before we go. So Terminus theorem. Sure. So Terminus theorem. So what does the theorem state? Right. Sorry for the connection. Right. So Terminus theorem, which is one of the several network theorems, states that any linear circuit, right? Any linear circuit connected between two terminals, right? Any linear circuit connected between two terminals can be replaced by a Thevenin's voltage, right? Replaced by a Thevenin's voltage in series with a Thevenin's resistance, right? In series with a Thevenin's resistance. Okay. So any linear circuit connected between two terminals can be replaced by a Thevenin's voltage in series with a Thevenin's resistance. So let's say I have this linear circuit. Let's say there is another source here. There's another component here. Okay. This is the terminal, right? Let's say this is the circuit diagram I have, right? On this entire circuit here can be reduced to a very simple circuit, right? With a voltage source and then just one resistor, right? Okay, so we can compress this whole thing or convert it to one single circuit of this sort. Just this, right? So that's what we're talking about here. This voltage source becomes our Thevenin's voltage, which we denote with VTH, right? Then this resistor here is our Thevenin's resistor, which is RTH. So any linear circuit connected between two terminals, and these are the terminals, so let's say A and B. Any linear circuit connected between two terminals can be replaced with a Thevenin's voltage in series with a Thevenin's resistance. Alright, so that's what we're talking about here. So there are rules you must follow when dealing with Thevenin's theorem. Alright, rules to find the Thevenin's voltage, and then rules to find the Thevenin's resistance. Alright, so I'll just take those rules and then. So finding Thevenin's voltage, which is VTH, right? So in finding Thevenin's voltage, the very first thing I want to do is to remove the elements. Alright, so remove the elements from. Alright, so the first thing is to remove the elements from the branch. This is to say, basically, open circuit the branch containing that element, which is that resistor that you want to find whether the currents passing through or the voltage across, right? So remove the branch, so remove the element from the branch, right? So basically, open circuit the branch containing the circuit element or whatever it is. It's definitely going to be a resistor in this case, right? So let's assume I have this circuit diagram. All right, so let's say this was in here. So we had a resistor at this side. Right. Now let's say I was asked to find the currents passing through this particular resistor, right, using Thevenin's theorem. Right. If I'm asked to find the current passing through this particular resistor using Thevenin's theorem. Now, we said the first thing you do is to find, or not the first thing, but to find the Thevenin's voltage, right? I must take this resistor from this circuit. So I must open circuit this particular part of the circuit, this particular branch, alright? So the next thing you do is to find your Thevenin's resistance. Okay. Alright, so we'll be dealing with the Thevenin's resistance, right? So to find the Thevenin's resistance, the first thing you do to find the Thevenin's resistance, so finding RTH, right, which is the Thevenin's resistance. So to find the Thevenin's resistance, the very first thing is to short circuit the branch containing that circuit element. Alright, So you short circuit the branch containing the circuit elements. All right. So if I have this as my diagram again, and let's assume this is where the circuit element is, right? As the whatever resistor we have to find its currents or whatever it is. Let's assume it's at this point, right? Okay, let me just draw it. So let's say initially it's here, right? Now what I do is I short circuit this part of the circuit, right? So I short circuit by erasing this from there, then so this is what I'll do too, right? So now it's assumed there is no resistor here, right? The effective resistor, sorry, oh sorry, so which we actually short circuit the voltage sources, right? Not that, right? We short circuit the voltage source. So that element still remains. Sorry. Yeah. Whatever is there still remains. Then short circuit the short circuit voltage sources. All right, sure. Short circuit voltage sources, and we open circuit current sources. All right. So you might have a circuit diagram which contains current sources. So you short circuit the voltage source and open circuit current sources. All right, sure. So let me use circuit diagram where I'll put voltage source and then current sources within. So let's say we have our voltage source here, probably have a current source this side. All right. Sure. So let's say we have a current source and then a voltage source within the circuit diagram, right? Now to find RTH, we would short circuit the voltage source, right? So this voltage source gets short circuited, right? And then the current source gets open circuited, right? Okay. So yeah, so this basically what we're going to do. So from there we find the effective resistance within this circuit diagram, right? and that resistance becomes RTH. I hope you get it. Okay, so you short circuit voltage source and then open circuit current sources. Then you find the effective resistance in this circuit. And that resistance is RTH, or the Terminus resistance, right? Now after that, whatever components we asked to find the current across, right? So we now have that components. So this is our RTH, right? Then the resistance of that component in series with it. Then all this in series with VTH. So this becomes the reduced circuit, right? This helps us to find the the currents across the resistance. Because the current across the terminus resistance is going to be equal to the current across the other resistor, and then the sum of voltage drops across these two resistors is going to be equal to the EMF that this would produce. Sure. Okay, so I think time is up. So probably next time we meet, we'll solve questions on